Okay. All right, ready, go. So now today we are going to start talking about models of discrete behavior. And in particular, we will deal with a mathematical model of behavior, which is finite state machines that are very much used in all kinds of different applications. So, for example, the screen of your cell phone is essentially governed or controlled by a finite state machine. Your vending machines, when you put the coin into the vending machine and the Coke comes out, is a finite state machine. So let's see how this works and what these objects are. So before doing that, I recall in general the definition of what an actor is. Now, an actor is a mathematical object. And we say, first of all, that a system is a function that accepts an input signal and yields an output signal. So very basic, very simple. So signals in, signal out. So the domain and range of a system function are sets of signals, right, which themselves are functions. So this one, in mathematical terms, is a functional view of the behavior of a system. Now, in general, we are used to think about a system like you give an input, and then you have a reaction, you see an output. Now, in the actor model, you see the entire set or sequence of inputs, and the output is the entire set of signals, of value of the signals. Okay? So it's from a function of time into another function of time. That's what the system does. Now, which is not the point-to-point input-output relationship. It's function to function. Now, why do we do this? Well, it's more convenient to deal with this model, especially when it comes to composition. And we'll see that not this time, but the next time. Now, on these models, functional models, you may have parameters, right, that describe a family of possible relationship between input signals and output signals. So, for example, you can have an amplifier. According to the level of amplification, you get a different output, right? So that is a parameter, is a position of a knob, right? So very basic stuff. All right. So the mathematical notation, you say that S, which is a system, the actor model of the system, maps X into Y, where X is a function and Y is a function. So we go from a space of functions into a space of functions. All right. Now, discrete systems. What are discrete systems? Well, discrete systems deal with discrete signals. Now, what is a discrete signal? The kind of intuitive notion is the fact that you don't have a continuum of values, but you jump, right, from one value to the next. And in general, our mind is used to think about a discrete model where there is a finite number of levels of the signal, but doesn't have to be that to be discrete. The only thing that cannot occur, that you have an infinite set of values between any 2 points, finite points. So that's the only thing that we have to worry about. So a discrete model, then, is something that maps a discrete signal into a discrete signal. Now, this one is an example that we are going to use throughout the class. That is a garage counter. So what does a garage counter do? Is that you have a finite number of spaces in a garage. You know that sometimes, for example, at airports, you have numbers, like, say, 22, which means there are 22 spaces in this part. When you see a red sign, say, don't even try to come in. There is no space, right? And this is what it does. So is this model that you see here. So now, what do we have to do in order to give an idea of how much space there is, if I can get in or not? Now, of course, there are two counters, right? So one counter is how many cars come in, right? And the other counter is how many cars go out. And, in fact, you see there arrival detector that has as an output the signal arrival, and a departure detector that has as signal a departure information. Okay? Now, what do we need to know? What kind of signal is arrival? Do we need to have a real number associated to it? No. We just need to know if the car is coming in, and same reasoning, the departures that we need if a car is departing. So that is the only information that carries is that I am there as a signal or I'm not there, which means a car is coming, nothing is coming. Okay? So that's called a pure signal. There's only two notions: is there, is not there. Okay? These are called pure signal. Now, by the way, you could encode a pure signal with Boolean algebra. So you can say nothing 0 is there 1. Okay? But it's not exactly that. Semantically, it's just the thing that matters is that this signal exists or doesn't exist. Okay. So, and in fact, there is a pure signal, and the counter up is a mapping from the reals, which is time, and the space that consists of two values, absent, present. Okay. Now, there is, of course, the down function is exactly the same. And the counter is something that sums whatever signals come in. Now, this is an algebraic sum in the sense that, of course, if I have a certain value, which means how many spaces I've got there, if the signal leaving comes in, then I have to increment by 1. And if the signal comes in and say oncoming, it has to decrease by 1. Now, this one is if you are interested in finding out how many spaces are left. Of course, you can do the opposite by saying how many spaces are available, right? So available, are taken. So you can go either way. Okay, so the counter is a function, in fact, that takes the time into absent, present in all possible combination, and is outputting absent, so no signal, nothing, which means there is no space, union n, so the set of natural numbers. Set of natural numbers is 1, 2, 3, 4, 5, 6, 7, 8, so on. And so that tells me how many spaces I have been taken in the garage. Okay? All right. So this is a mathematical model, what happens. Now, what we want to say is now the concept of reaction, right? Reaction is another intuitive concept, right? So you get something in and you react to it, right? And in fact, most of the embedded system of interest are reactive systems. So they sit in an environment. If they see something that the environment produces, then they react to it, okay? So, for example, a reactive system is your braking system in your car, right? So it sits idle, then you press the braking pedal, and it reacts to the fact that you have pressed the braking pedal. So when a system reacts, it does two things. It changes its state, and it produces some output. Okay? So in the case of the example of the car, if you press the braking pedal, then there is an actuator that takes that pressure and translates into pressure on the disc of your wheels. Okay? So that's an output. It's the command that is given to the actuator. So in this particular case, the possible outputs are the display of how many spaces are left or how many spaces are taken, either way. Okay. Now, when we say changes in his internal state, right? So we have this notion. It's always very intuitive, the notion of state. So I'm in a particular state. So right now I'm walking. I am in the state of walking. I stop. I change my state from walking to standing. Okay? So that is describing what the system, where the system is. There is no output. The state, the concept of state, doesn't have associated an output. It's a separate function. It's a separate thing. So in a mathematical model like this, you have to give two information: where I am in terms of the mode in which my behavior evolves, and what is my output. Okay. So that's the notion of internal state. Then we'll see later mathematically what a state is in more precise terms. Now, of course, input and outputs are always defined at a reaction. So when something happens, when you have a set of outputs. So we said before that the inputs are in a state, take value in a particular mathematical domain. So in this particular case is the set of functions up and down into absent present, right? And so in all the possible combinations that are feasible. And the outputs are also into a set, which is the mapping of the signal, which is count, into absent union natural numbers. So this is what we already said, but this is specified separately. So a practical parking garage is a finite number of M of spaces. So we can assume that a coding of the state of that particular system that is the garage is the number from 0 to M. So that represents our full I am as a garage, right? So it is an intuitive notion that is state of the garage. So states 0, 1, 2, to M. All right. Now, how can I capture this thing into, yes? Say it again.
Is it always the case that we define the state to be equal to the output space? So in this case, for example, 0 to M is basically the possible values of the output.
Is a choice of encoding, but it's not always the possible, meaning that the state is a different concept, right, than the output. So, for example, assume that the output is a real number, right? So, for example, the speed of the car, right? But the state is I press the pedal or I don't press the pedal. That is a discrete, right? So, but the output is continuous, right? So if I associate the state to the output, then, I have an infinite signal, and that's not so good, right? So they are really separate things, right? Sometimes people, there are cases in which it's convenient to represent the state as an output. Now, is there only a way of describing a state? No. You have choices, right? But the most important thing is that, if you remember from ordinary differential equation and the like, and linear system theory, a state is essentially a summary of whatever has happened to the system before, right? So the interesting thing is that in a linear system, what you can say, or also whatever signal that is describable by a first-order differential equation, that to find out what happens to your system in the future, the only thing you need to know is where you are now plus the input. So you don't care about what happened 2 years ago, right? Because all of that is into that state, right? That state is a summary of all the information I got. Okay, so in this particular case, I can encode this information about the mathematical model that we were saying before into this notation. So the notation is made of nodes, and every node is associated to a state, and then arcs, and the arcs are associated to the transitions. So when I go from one state to the next, I say, from this state, I can go here. Okay? So for example, again, in my motion, I can go forward. Okay, so there is a state. Alberto is moving forward. The next state is Alberto is standing, and the next state again, Alberto goes backward. Dangerous, right? Okay, so that are the three potential arrows, right? So if I'm going forward, it's difficult that I go immediately back. You can imagine that I'm forward, stopping, back, right? So the transition is that, right? If I were really an acrobat, I could do this very fast, so I don't need to go through the standing. So there will be an arc that goes from the state walking forward to the state walking backward. So that arc is representing what happens, right, to my state. Now, what will be the label that is associated to this moving from one state to the next? What is the reason why I'm changing one state to the next? It's because there is an action, right? So I'm reacting, right? So there is an input, right? So the input is the trigger. right, of this change of state. And in fact, these labels, these arcs carry a label that says under what condition I go from here to there. Okay? Now, it's also convenient to associate to this arc also the value of the output. Okay? So in general, for finite state machines, you have two fields associated to the arc, to the transition. One field is the condition under which you move, and the slash, what the value of the output is. Right? Okay. We'll see later on that there are machines in which you, to find out what is the value of the output, you have to sit on the arc. And there are machines in which you can associate an output always with the state. Okay? But there are two different kinds of machines, and we'll see later what is the difference between the two machines. One is called the Moore machine, the other one is called the Mealy machine. So anyways, so what is the condition in which, in this coding, I'm moving from state 0 to 1? Is remember that the encoding of the state is the number of space that have been occupied. So for going from 0 to 1, of course, there must be a car that comes in, right? Now, is that the only thing that I need to worry about? Now, this one, I could indeed make a state diagram like this, in which I only look at the presence or absence of up or down, right? In this particular case, you see that the guard, so the conditions that I put on the arc, is actually a logical expression in which says up, so a car is coming, and not down. What does that mean? That a car is coming in and no car is coming out. Now, in this particular case, we have to have a notion of simultaneity, right? So if a car simultaneously comes in and comes out, then the state doesn't change, right? It stays the same. There has been an action, but the system has not reacted to it. It stayed into the previous state because +1, -1, same, right? Okay, so that is the reason why you have that condition. Now, what is the /1 is the output, because there is a display that tells me how many space have been occupied. Now, in this particular case, you say, well, gee, 1 is state 1, so it's associated 1 to n. Special case. Okay. Now, so this is also important to figure out that there may be transitions that I don't tell you about. And the transition that I don't tell you about in this diagram is when up and down are present at the same time. We said already that when input and output are present at the same time, nothing changes, right? So how would you code that information? What would you put in that diagram to give that information that is up and down are present at the same time?
You have a reaction where it transitions to its...
Very nice, very good. So it's called a self loop, right? So you don't move, right? So big information. But if you don't say it, it means that the finite state machine is incomplete, meaning that I don't give you the transitions for all possible combination of the inputs. But in this particular case, it's incomplete, but it's obvious how to make it complete, which means all possible combination of input and outputs, I have always a transition that tells me what happens, right? It's just I chose not to put it down because it's trivial, okay? There are some machines that are incomplete, and the notion of incompleteness could say, I don't care. These things that I don't want to know about, because they are never going to happen, right? So they're not there. Which is very interesting, because actually, when I say this particular condition, I don't care what happens, is a freedom. Since you don't care what happens, I can make it do whatever I want, right? And so it's a degree of freedom, which I can use to optimize my design, okay? All right, so this one is obvious, right? If the counter up is incrementing, or 1 to up to m, and then you are in m, there is no space available, or you reach full capacity, and so it doesn't make sense to say that an up is coming because there is no space. So actually you would have a bar that is preventing the new car to come in, right? So it stays there. until someone leaves. And when someone leaves, you go to state m minus 1. Okay? This is very simple. I don't think that there is any doubt about this. Now, the interesting thing is that the really interesting thing is that condition that tells you what happens when certain environment variables change. So some inputs change. And they are called guards because in some sense they are sitting there like this, and they prevent your system to move unless that condition is verified. That's the reason why they are called guards, right? And guards are logic formulae. Now, of course, the most trivial logic formula is the simple value of a variable, right? That's the simplest possible guard. But there could be any possible logic expression of the input variables, right? Okay. In this particular case, is an AND and a negation. Okay, so this is the guard. It's specified using the shorthand up and not down. So we already talked about that. Now, there is another important point, which is the notion of initial state. Now, in this particular case, I put 0 over there, and I assume that my system starts with no car spark. So that is my initial information. Now, if I don't give you the initial information, can you say what happens to the system? Big question mark. Can I? Or I'm stuck? Is it essential to give an initial condition? Yes, right? It is absolutely essential. Because remember that the state is information what happened in the past. So if I don't tell you what happened in the past, where the heck do I know where I am? Right? So you must always give an initial condition. Now, mathematically, if you have x dot equal to f of x, you cannot solve a differential equation unless you have an initial condition. Right? Same story. It's exactly the same thing. So it's nice that if you look at mathematics and if you look at physics, like in this particular case, the garage open school, they carry the same information, right? So mathematics reflects what happens in reality, and there is a one-to-one correspondence between the mathematical concept and what you intuitively need to do in order to be capable of telling what the garage is doing. So the initial condition is always very important. Now, I don't know how many of you has done a class on computer architecture of computers, but there is an interesting point. Now, of course, all of you have got a blue screen, right, on your wonderful Microsoft system. Now, less frequently, okay? It's not as frequent as many years ago. But you get the blue screen, right? And then, and then, boom, black, right? And then, rebooting. Now, what does that do? It's bringing you to a known state, which is a reboot state. So switch everything off, start from 0, okay? What do we do when the TV set doesn't work? Unplug. What do? We set the initial state, okay? So that's it. So the initial state is important. You cannot do anything without the initial state. The output, we already said, is a way of labeling. I mean, we can say what the output is by labeling the transition. And the mathematical model, we can do all the set theoretic, yes. Yeah. Well, it depends, because suppose that you are in a state, right? And then the output changes, right? What does that mean? Something else has happened, right? So otherwise I have a non-deterministic system, right? So which means that I have to introduce another state, right? So my encoding of the state is incorrect, right? Or you can say, well, in this particular state I can have a sequence of outputs, but then I would label that with a sequence. 0, 1, 2, 3, 4, whatever. Right?
But once you arrive on that state with the output just,
arrive at that state, yes.
Would the output just go back to absent or?
No, no, because the 1 the output 1 is telling me that one space is taken, right? In this particular case, unless it goes down, it's still taken, right? But this is an important point. Okay. Now, because it's the semantic that you associate to the signal, right? Now, for example, when you have a sensor, a D to A converter, right? You have different models, right? A D to A converter, what happens? That you have a digital thing, right? And you convert it into an analog, right? And so what happens is that you, for example, is some signal, and then you put it in the real space, right? Now then, since it's discrete, you wait some times, then you have another point, right? Now, how do you go from here to here, right? Electrically. So what happens to the electric circuit? Any idea? There are two ways of doing it, of course. And one is called sample and hold, and the other one is just simply sample. Right? Sample and hold, what does it mean? That the value is maintained, right? Which is like this, right? So the output is maintained. It stays at that level. Then a new thing happens, and then I go up. So it's like a staircase, right? Other times is that, okay, this is the value, and then chunk, I go down to 0, and it's another value, boom, and I go down to 0. This is not sample and hold. And there are two different circuits that do the same thing. So they are both A to D converters, no, D to A converters, but they operate in a different way. So in general, the most used model is sample and hold. So you keep the value there, right? In this particular case, now, this is a semantic of a problem, right? So we know that one is a state. I mean, in this particular case, the output is the state, right? So it's a semantic of the thing. But you could have, for example, well, assume that there is no, this also will stay constant. Okay, suppose that you want to know how many. Okay, if you can cross a street, right? Now then, the car goes by, the counter goes up, so I cannot cross the street, but immediately after that, I go down to 0, I can cross the street, right? So the output in this particular case is, it doesn't hold, right? So it's not that once it's there, I cannot cross the road forever, right? So this is but it's a different semantics. So according to what you encode in the model, you have different situations. Okay. So now, then, the mathematical notion is that you have a set of states, and this set, to be a finite state machine, has to be finite, right? Finite number of states. There is a space of inputs. In this particular case, since we use the actor models of systems, these are functions, right? The input is input function. Now, the output, same thing, are output functions. And then there is a infamous function here. It's called update, right? The update is what makes me do a step in the finite state system and what produces the output, right? So that's update. So I'm updating the behavior of the system. Now, the update is also called the transition function, also sometimes improperly, because the transition function is simply telling me if I'm in this state and this condition occur, what is my next state, right? So that's the next state function, or the transition function, okay? And then there is the output function that tells me, given this input and given this state, given this state and given this input, this is my output, okay? So which, in principle, and should always be so, is a different function, right, than the next state function. Sometimes they can be merged, as we said before. For example, in the case in which I can encode the states with the output, then it's the same, right? That doesn't make any damn difference. But in general, it's not the case. So from states cross inputs, you go to states cross outputs. Okay. Now this is finite state machine notation. So you have states and you have guard and action that are associated. Notice that the output sometimes are called actions. So it's what the system does when it takes the transition. So you got guards that tell you when you can take the transition, and action that corresponds to that transition. Now, there are sometimes graphical notation to tell you what is the state 0, the initial state. And in general, is a double line, right? So if you have a circle, you have double circle. If you have an oval, you have a double oval. And that tells you what the initial state is. Because now we say state 1, state 0, this and that. And so it's easy to say, oh, okay, this is the initial state. But very often, when you do designs, you give the states not a number, but you give it a semantic notation. So maybe I'm standing, I'm moving, this kind of thing. So the states are not labeled state 0, 1, 2, 3, 4, right? Also because if you want to document what the heck this finite state machine does, it's better to be descriptive, right? So every state should tell you what the meaning of that state is. And so in that particular case, unless you specifically indicate what is the initial state, then there is no way that you can infer it by looking at the label of a state. Now, these are examples of guards on pure signals. Pure signal meaning, again, we are working in the Boolean space because there are only two values in this space. True means the transition is always enabled. So you have 1 over there means, okay, I always take that transition. So there is no constraint upon the changing of state. Now, P1 says that transition is enabled if the P1 is present, so the pure signal is there. So not P1 is that I take the transition if P1 is not present. P1 and P2 means that transition is enabled if both P1 and P2 are present at the same time. P1 or P2 means that I take the transition when either P1 or P2 is taken. Now, P1 and not P2 means, of course, when if P1 is present and P2 is absent, then I take the transition. Okay. So that we already discussed that before, but just to summarize what we say. Now, sometimes I told you there are inputs and outputs that are not pure signals. They are numerical values. They can take... The states have always to be finite, no? Otherwise you don't have a finite state machine, okay? So, but the input and outputs can belong to the reals, right? So I can say P3. So transition is enabled if P3 is present. P3 equal to 1 means I take the transition if P3 is present, but is also equal to 1. Okay, so I give an information there. Now, the important thing is P3 larger than 5 means that I'm going to take that transition only if the signal P3 is present and is larger than 5. Okay, so I can associate inequality and equalities on the guards of the finite state machine. Now, this one is a thermostat. It's an example where the information about numerical value is important. Now, this one is a finite state machine that you find when you go in your hotel. And, you know, sometimes I go crazy because they are not so well adjusted. So what happens is that you said, okay, I would like to have 70 degrees in my room. And what happens is that you go 71 and then boom, cold air. Then 69, boom, hot air. And then you have a heart attack because you keep on getting cold air and hot air in a very short sequences, right? That's a controller action that is not so very good. Anyway, so this is exactly the same. So what you get is that you stay in the cooling stage as long as the temperature is larger than 18 degrees. So I keep on blowing cold air until I reach 18. Then if the temperature is less or equal than 18, so I reach the threshold of 18 centigrades, then I go into heat, right? So I heat my room. Now, as long as the temperature is less than 22 degrees, then I blow hot air. Now, notice that is 18 and 22. Why is that? To prevent what I said before. Now, if you go to some hotels or motels or dingy places, then this is not well set. So you have the two boundaries are too close, and then you get this phenomenon of bing bong, bing bong, bing bong all the time. Now, 1822 is enough to have some respite, especially during the night, but the thing is not blowing, right? Okay, so that is temperature less than 22, you stay in heat. And, of course, if the temperature is larger or equal than 22, then you go into the cooling mode, and you stay there until the temperature is larger than 18 degrees. Okay. Now, it's interesting because this particular finite state machine has a self loop that keeps on going, right? So it keeps on staying in a particular state for a while, right? Until that numerical condition is verified. Okay. Now, where does a reaction occur? So suppose that all inputs are discrete and reaction occurs when any input is present. Then the transition that you see there will be taken whenever the current state is S1 and X is present. So now, what this is what we call an event-triggered model, which means that I'm changing state when something happens, and as soon as it happens, I change state. That's the reason why it's called event-triggered. So my transaction takes place when that event is occurring, right? Now, this is the best, right? In terms of application, is a nice thing, right? Now, there may be a situation, and my God, it did happen. So this is a history, real story, that there was a controller of air conditioning in a car, right? And so you know that the air conditioning in a car, you have the up and down, right? So you can set the threshold, increase by 1 degree or decrease by 1 degree. And so this controller is very simple. It was implemented in an Alfa Romeo car. Well, that was like 15, 20 years ago, so no problem now. But they had one thing, the designers forgot to specify what would happen when the up and down arrow would be pushed at the same time, because nobody was thinking, who is so crazy to do that, right? So they didn't consider that there are children in a car, and they love to push all buttons in any sequence, right? And so guess what? When the system went bananas, you had to reboot the car, so you had to restart the car. Not a good idea, okay? And so that is the reason why it is important to think that event trigger may be good, maybe not. Why? Because the event triggered, you have two events that occur at the same time, and you have two reactions that are enabled at the same time. So the system, I don't know what to do, and it shuts off, right? So not good. So event trigger is good in general because it's the fastest reaction, right, to what happens outside. But you got these horrible situations that sometimes create havoc, right? So instead of event triggered, there is another mechanism that is called time triggering. Now, anyone volunteers how you could specify a time triggered behavior? Notice that event means something happens, I react immediately. Time triggered, time is involved, right? What happens is that the transition is taken, some input is changed, and time has reached a certain value, right? And so that is time trigger. So I can only make transition at specified times, right? So this still, in the previous example, I can still find a way of tricking the system. But in general, what happens is that if the two signals occur together inside this particular thing, I'm not reading them, right? I'm not considering them. When the trigger comes in, which is a time trigger, then I read the value that is in there, and I could have already, taken care of this inconsistency, right? So nothing happens. That is the difference between event trigger and time trigger. So event trigger is, as I said before, is the most intuitive, is the fastest reaction that you can dream of. It can yield to problems, like we said before, of a two-button push at the same time. There may be a sequence of commands that come in really very fast, one after the other, which are contradictory, and you may enter into very bad behaviors, right? So that's the reason why, in general, time trigger mechanisms are safer. And so when you have safety critical system, you prefer to use time trigger architectures or protocols or whatever you want to call it. Yes? Yeah, well,
which happens in that slot between.
You don't see anything, okay? Because, so sometimes This is something that I fired many graduate students upon this thing. Sometimes people say that the transition takes 0 time, right? And the communication takes 0 time. It's not so. I mean, it's stupid to say so. It doesn't matter. Why? Because what happens between this and this, I don't see, right? It's not there, right? So I see only the effect of that at a particular instance, right? And so remember this, okay? So because this is the essence of your question, right? So I don't see anything in there because it doesn't matter. It doesn't exist in my model, okay? Now, then the interesting question is that, what do you think the word is? The word is event-triggered or is time-triggered? Well, of course, if we go down to the nanosecond, is a different stuff. But assuming our normal life, our environment is event-triggered or time-triggered? Any wild idea? You could make both, but principally, mainly, the natural behavior of our is event-driven, right? So, for example, anything which event-driven is also, you could also say that is an asynchronous system. Asynchronous, so things happen whenever they want, right? And they are not lining up. Now, the notion of time-triggered or synchronous system is that you line up things, right? You make sure that things are lined up. So you order things, right? So you make a disordered world more ordered. So you eliminate entropy, right? So you try to take entropy away. But indeed, as we said before, the world is asynchronous. So the world is event-triggered. It's not time-triggered. And so now the point is that how do you implement a synchronous model? Now, when you implement the synchronous model, right, you have to figure out ways of making an asynchronous world synchronous. So what would you do? The clock, right? The infamous clock, right? The clock is a reference, a time reference, that produces that trigger. It's still triggered, right? It's triggered. It's event triggered, but on one particular event. That is the clock, right? So, and that is a way in which you trick an essentially asynchronous system to behave synchronously. But when one of you tells me that a synchronous system, when there is a clock, you are fired. For sure. That's nothing to do because this model, the finite state machine model, is without time. There is no notion of time in it. The notion is transitions, right? Is that what matters in a finite state machine is the transition. There's no time whatsoever. Now the clock you use to implement a synchronous behavior, but it's not the synchronous behavior. It's a trick, okay? It's an implementation fiction, right? So it doesn't exist in some sense, right? So you make it do that. All right. So a reaction occurs whenever something is presented to the input, okay, of the system. Now, suppose that x and y are discrete and pure signal. When does this transition occur? The environment triggers a reaction and x is absent. If this is a complete event trigger model, then the transition will never be taken because the reaction will only occur when x is present. Right? So otherwise, it doesn't know what to do, so it stays there. Okay? Now, when you have a clock, you know, the why clock sometimes is a horrible thing to do. Horrible meaning is wasteful, right? So to have a clock, you have to have the cycle of a clock, right? So the cycle of a clock is a regular period, right? So every so many seconds or so many nanosecond, picosecond, whatever, you have to give it ping an input, right? Now, suppose that I sleeping, right? Nothing happens in the world. It's just I'm sitting there, doing like this. And then the clock comes in and ping. I wake up, I do something, stay there, nothing happens. Boom, goes back to sleep. Ping! Aha! Okay? So every time you do ping, you know, circuit work, power is consumed. to do absolutely nothing, right? And so when you study what the cycle is, you have to balance the fact that you want to be able to catch signals when they come in, and at the same time you don't want to wake your system up too often. So when you have a time trigger protocol, for example, for wireless communication, TDMA, right, time division multiplexing, you have tricks of all kinds of sort in such a way that not your entire node wakes up when the clock comes in, but only a small tiny piece of the circuitry. Now, if that circuitry detects something, then ta-da-da-da-da-da, it wakes up everybody, right? But if nothing happens, it's only that small piece that goes up and down, so power is optimized, okay? So, for every solution, there is a downside and there is an upside. So, you got to choose which one you care more, right? So, is efficiency or is safety? This is the trade-off. Efficiency, event trigger, safety, time trigger. Okay. Now, when does this reaction occur? Suppose all the inputs are discrete and a reaction occurs on the tick of an external clock. That is a time trigger. We already said that the key event that allows me to, the key guard, right, that allows me to move from one state to the next is the clock. So the clock is always ended with all the inputs, real inputs to the system. And so the clock is down, nothing happens. The clock is up, I do something. Okay. Now the default transition we already talked about is when I don't tell you what is happening, right? So in the case of the car coming in and coming out, we say that the state would not change, but I didn't indicate it with a self loop, right? Saying I'm staying there. Now, when this is a default transition, so I'm not telling you, but it's there and it's obvious what it is, and so it's hidden. It's a ghost transition, whatever you want to call it, but it is there. And so these are also called default transition. There are many ways of calling it, so default is as good as anything. Now, the important thing is that in general, it's a good idea to show the default transition if I produce outputs, of course, right? Because I have to have a place where I'm going to put the output on, and so I show the transition. Nothing is changing, but it's producing an output, so I show it. So in this particular case, you see, is a traffic light controller. I'm sitting in green, and there is no reason why I should change from green to yellow. And so I'm sitting there, but I keep on outputting green, right? So that I need to say. Same thing, yellow, nothing happens, so I stay there. So there is a default transition, but it has an output associated to it. I may as well display. This is a particular case where it doesn't have to be shown, because if you use the control, which is a pure signal, yes? Say it again.
If the output has, by that argument that if you want to show that outputs remain switched on when you're in a particular state, right? So in the garage counter example, right? If we are implementing the old semantics.
Yes. So if you want to have a complete finite state machine, yes, I should. So if nothing happens, in fact, not up, not down, I stay there, right? And so that would be an explicit default transition, okay? But in that particular case, if I assume that the display of the counter is a persistent signal, then I don't need to show it because my output is not changing. Okay. And also, in this particular case, notice that I put the signal, instead of saying heat, right? I just say heat on, which means I switch the heater on, and then it stays on, right? And so I don't need to tell it because the signal already encodes the notion that I stay there. So that is the reason why I told you guys that anytime you have a problem, right, and you want to encode that problem with a particular mathematical notation, there is not a single unique way of doing it. There is a better way of doing it, but there are many different ways in which you can do it. Right? And so it's up to you, the creativity or the quality of a good system-level designer is to find the right encoding of the problem. Right, quote-unquote. I mean, the efficient encoding of the problem. And efficiency is related to number of states, a number of transitions, that kind of stuff. Okay? So this is, again, is not a God-given. So it's, as always, a model is a representation of reality. A representation of reality you can have in many different ways. Now, there are a few definitions about finite state machines that are useful when you read the literature. Sometimes they contain this information, so it's good to say what they are. So, stuttering transition. So, stuttering transition is potentially an implicit default transition that is enabled when inputs are absent. So, for example, when you have if you think about the time trigger model, you could qualify a stuttering transition. When the clock comes in, nothing has happened, I keep on looping on myself. That's stuttering. So it means that I don't do anything, right? Sit there, doing nothing. Okay. Now, receptiveness. A finite state machine is receptive if for every change in the input, something happens to the finite state machine. So some kind of transition is taken. So if I want, for example, to detect fire, it's better to have a receptive machine. So which means that if I have a fire, the thing wakes up, right? And does the noise that we are all expecting to do. If there is nothing, we don't want the siren to go off, right? So this is receptive, meaning that no matter what happens, I always have an answer, right? So that's a receptive machine. A finite state machine is deterministic if given a state and given an input, there is only one next input, one next state I'm going to. Okay? Now, I could represent a real problem also as a non-deterministic finite state machine, which means of the same input I can go to two different states. Now, that will be interesting because if I want to know what my system does, for a particular input I can go in two states. Now, if I want to know all the possible states I can reach, I have to keep two traces, right? I have to look at the finite state machine under two potential choices that my machine has taken. So it makes life more miserable to find out what the system does, what is the advantage of doing non-deterministic finite state machine. You can compact the representation, right? Because I'm trying to eliminate things that I don't care about, right? So, and we'll see later on what we can do. And in fact, there is a bunch of theorems that say that if you want to eliminate non-determinism, you can have an exponential blow-up in the number of states. And then there is a famous construction, which is called the Rabin construction, that transforms any non-deterministic finite state machine into a deterministic one, but is exponential. So essentially, you have to make all the possible combination of next state as an additional state, right? And so now you have 2 to the n potential additional states, where n is the number of states where I can go from this state. All right, so determinist we said. An example of a non-deterministic finite state machine is this one. The two red arcs are transitions that are taken under the same input. So I can go either in that state or I can stay in my state. So, for example, suppose that I have a traffic signal which is triggered also by the presence of a car, right? So, for example, I'm in the famous country road problem. The country road problem is that if you have a standard traffic light which works on time triggered, right? So every so often it goes from red to yellow, from red to green, to yellow, to red, to red, always like that. But people get very antsy because on the side there is no car comes across, so you have a bunch of cars sitting there waiting for the signal to turn green, right? And there is no need why that signal should be red, because there is no car on the sides. So there is a sensor that detects if the car is there or not, right? Now, it so happens that as soon as a car comes in, it's not that you switch immediately to green on this side, right? Otherwise, you have a pile up you wouldn't believe, right? So you go into a waiting state. So you wait to see what happens. Now, that waiting state, right, is a different state, or you can stay in the same cycle, and that is what the two red arrows are telling you, that under a particular event, you can go either to the next state or stay in the same state, in this particular case. So behavioral traces. We were talking about the behavior of a finite state machine. What is the behavior of a system, right? The behavior of a system is what a system can do, right? So it's, and I exhibit a behavior, meaning that I see what I do over a period of time, right? Under a potential sequence of inputs. So a behavior, as it says, is a sequence of non-stuttering steps. Now, what is a trace? A trace is attached to a behavior and simply recording all the values, state, input, and outputs. So it's a sort of black box for airplanes, right? A black box of airplanes do exactly that. They take a trace of the behavior of a plane. Now, a computation tree is actually a graphical representation of all possible traces. So it's like you have a finite state machine and you flatten it out, right? For every possible input, you show where the next output is, and for every combination of input, you have to branch out, right? And so it's a linear graph. It goes like this. It has no loop, right, except for a final loop that comes back to the beginning. And is much, much, infinitely bigger than the finite state machine. The finite state machine, if you think about it, is a very complex way of representing a set of behaviors, right? You represent this set of behavior by the rules that you have to follow to create the behaviors. If you want to know what happens to the system, you apply the input in sequence and you see what the system does, right? And so you are exploring one behavior. You are taking one path into this computational tree, okay? This computation tree. So the beauty of state models is the fact that they encode in a finite way an infinite number of behaviors. Potentially infinite number of behaviors. So now, finite state machines are in general very good, especially when it comes to check safety properties. Now, safety properties means that no matter what sequence of input are coming in, you are not falling into a bad state. A bad state when, say, well, engine blows up, right? That's a bad state, right? Or airplane crashes. That's a very bad state, okay? So you want to show that under possible set of inputs, all possible things, you never get to a situation where the car or the airplane crashes. Now, in a finite state machine, you can investigate the behaviors and see whether you hit the bad state or not. If you never hit the bad state, then you're cool, right? My design is safe. So safety properties are checkable in finite state machines. So we are going to see, towards the end of the class, methods to do this reachability analysis. So you analyze what can be reached and what can never be reached. So the safety properties are bad state, you never want to go there. There are another class of properties that are the liveness properties, in which you want to say that I always can get to a state. Okay, so it's a complement of what we said before. Now, that is much more complicated to verify. Right? Liveness is a beast, right? Safety is much simpler as a problem in itself, and there are efficient algorithms to do so, even though are efficient but not cheap by any means. So, yes?
How can you decide that you don't ensure you're not going to get to a state if you're not coded for that state? So, like, is it like you code for a state that you don't want to get into? Like you
yes,
say
of
you
course.
have a state,
yeah, I give you the finite state machine that describes the behavior of a system, right? Then I give you the set of bad states, and I have to tell you what these bad states are, right? Yeah. Now, the point is that when you actually compute on this finite state machine, there are data structures that are particularly efficient, right? So that you can compute really fast next state function, right? So you want to show that for n transitions, in your next state function, the bad state is not. Okay, so that's the story. Okay, and so you don't know because it depends on the initial state and on the sequence of inputs. So if the bad state is isolated, there is no transition that takes to there, then it's trivial, right? But sometimes it's very difficult to determine. I mean, you don't have a graphical representation, right? Because it would be too big. And so you have an encoded representation and short representation of the next state function. And so in order to see what are the states and if you reach the states or not, you have to apply this next state function starting from the initial condition. Okay? So, and then you can prevent some inputs from occurring that will not take you to the bad states, right? So the controllers do that. A controller, what happens, what do they do is that inputs come in, and then I prevent the finite state machine to go into states that will lead me eventually into the bad stuff, right? So I cut that off. For example, I don't know how many of you have followed the story of the American Airlines plane that went down in New York, right? Well, that was a bad state reached, right? So what happened is that, and the controller was not taking you to the bad state. The interesting thing is the man, the bad guy was driving, piloting the plane, they took to the bad state. Why? Because the plane was going up at too steep an angle, lost lift, and so what the automatic control did is that to say, if you do like this, we are going to go into a stall and we are going to crash. So how do you increase the lift? You nose down, right? You go nose down because you increase the speed, you get the lift, and then you go up again, right? But you had the turkey pilot, and the turkey pilot saw the plane doing like this, we are crashing, and was taking up, right? And the more the plane wanted to go down because it was losing speed, the more the guy was taking it up, and the more speed it lost until, boom, stall, catapult, right? So the controller was preventing you to go to the stall, right? And so the controller was changing the state of the system to avoid to go into that state, right? So that's what controllers do. Now, also tells you that if you have two controllers that don't agree, then disaster always strikes, right? Okay, so don't do that. Or teach the pilot what the guy is trying to do, right? Okay, so that is an example of how design is important. Design for safety is really important. And how it is also important to model the environment. And when you talk about environment, it's not only the environment, meaning the speed of the air, but also the turkey human. And so why autonomous driving is so very good? Because we take a human out of the loop. So 99.99% of all accidents on streets is because the driver is drunk, the driver is texting, the driver is upset, the driver is a heart attack, whatever, the driver. Take the driver out. Okay? So that's my recommendation. Take the driver out. I'm much more confident about these machines than the driver. Okay. So use of non-determinism. There are two ways of using non-determinism, which are very important and interesting. The first way in which you use non-determinism is to say, I don't know. So, for example, right now, I don't know if she's going to stand up and hit me. Right? Good, right? Why not? You get chunk. Bad professor, I don't like it. Chunk. Right? Okay. So, if I don't know that she could exhibit that behavior, then I don't take into consideration. If I want to be super safe, I'll take a distance, right? So that I can react. Right? So it's non-determinism. So I have to say, she is possibly going to hit me or possibly staying in her seat. Maybe fall asleep, but, that's okay. It's not dangerous to me. This is a non-determinism, right? Because I don't know what she may do, right? I don't have direct control, so I don't know. And so non-determinism is that under these particular conditions, she can react this way, the other way, okay? Now, the other way in which I can use the non-determinism is because I have not decided yet. So I want, for example, to have an implementation of a system that does something, and I've not decided yet if I'm going to take this particular implementation or that particular implementation. It's not that I don't know. I have not decided. So now, assume that you want to establish safety of the behavior of your design. So how do I take care of this non-determinism? I have to check all possible behavior that she's going to exhibit, right? And then I have to say that for whole her behavior, I'm fine, right? So take the distance. Right? I'm fine. Don't worry. That's one. That's the way in which you deal with what you don't know. And what you have not decided, if you want to check a safety of your design, the thing that you have to say that there exists an implementation, there exists a determinization of my finite state machine that is safe. So for her, I have to use for all her behavior. For what I have not decided yet, I have to say that there exists at least one decision that is making my system safe. And then, of course, I'm going to choose that, right? But you see the difference. There is a semantic difference in using non-determinism to say, I don't know what happens, and what I've not decided yet is a degree of freedom. Now, in this case, it's not a degree of freedom. It's actually taking away degrees of freedom. The other case is representing degrees of freedom. Okay. We say that already. Non-deterministic finite state machines, of course, are more compact because if I wanted to display all possible behavior that she may have, I may have a humongous, I don't know how many behavior you can have, but I assume many, and all possible gradation, right? From very bad to very good. Right? And so I have huge amount of states, right? That I have to. Instead, if I say I don't know, it's more or less like this, right? So I clump all this behavior into one, and then I'm using non-determinism to represent what she may or may not want to do. So that's what I said, the potential exponential. Non-deterministic behavior, of course, I can build a tree of computations for non-deterministic behavior, and I have to see what happens for all possible situations that corresponds to different choices that I'm going to take into the finite state machine, which is a royal pain in the neck, right? So the point is that non-determinism is very good to represent. It's very bad when you want to do things on it. Okay, so that's very bad because you always have to determinize it, right? So it's good for representation, but then when I want to do something, I need to explore all possible conditions and choices. Donc, related points. What does receptiveness mean for non-deterministic finite state machines? Question for you. Think about it and then come back to me. Now, notice that non-deterministic doesn't mean probabilistic behavior. Okay? Now, there are things like probabilistic finite state machines. And what are probabilistic finite state machines? They say that now I know a little bit more about her model. And so I say there is a probability 0.01, I hope, that she's not going to hit me. And there is a probability, say, 10%, that's 0.1, that she's going to fall asleep. And there is probability 9, at 0.9, that she's going to be nice and quiet and following the lecture and being a nice person. Okay? So that is a probabilistic model of her behavior, which is not non-deterministic. Why? Because I know what are the conditions under which she behaves this way, the other way, and so on. So probabilistic doesn't mean non-deterministic. Okay? It's deterministic as deterministic can go. Okay? Yes?
So would you model a computer as a finite state machine?
The controller of a computer, yes. Not the entire computer is...
what about a quantum computer? Would you model it as a non-deterministic finite state machine?
Of course, because some of the phenomena are based on quantum mechanics, so it's not non-deterministic. It's highly statistical model. It's statistics. It's governed by statistical.
But that is a probabilistic
phenomenon.
finite state machine.
What?
That is the probabilistic finite state.
Yes, exactly. It's not non-deterministic. It's probabilistic. The quantum computing will be a probabilistic. Because this transition can be taken with this probability, this transition can be taken with this other probability, and so on. And so the question to ask to a probabilistic finite state machine is, say, if I give this input, what is the probability that I'm going to this state?
But it's not a non-deterministic.
No, it's deterministic. Because probabilistic means, it's essentially non-deterministic, as I said before. I don't know. I really don't know anything about it. Probabilistic, I know the model, right? I know the probabilistic model. I know so.
So probabilistic finite state machine is still deterministic.
Yes. Yes. Yes, indeed. Because I have a model, right? I know what happens. Because the probability that I associate with a transition is characterized. Now, in the non-deterministic finite state machine, I have no idea. I can go here. There.
You have no idea means it could be random, it could be like normally distributed.
Could be, but it's not. I don't know, you see. That is the difference. Non-determinism means I don't know. Nothing about it. Okay? Probabilistic, I know the probability. I know something. Right?
Even if you flip a coin, it's still deterministic.
If I flip a coin, is deterministic, but it's probabilistic. Because I have a distribution.
Could you give an example of what is a non-deterministic?
As I said before, the behavior she is exhibiting, I don't know what probability she's going to have. For example, suppose that I drive a car, right? And what is I don't know what may happen of the mountains, right? There maybe a big boulder that comes down and hits me, right? How do I know? I have no notion of a piece of rock coming down, right? And so that's non-determinism, right? I don't know. Could be, could be not. After you model, it becomes probabilistic. So what is the probability of the rock hitting me? Boom. And in fact, for example, the insurance companies, they work on probabilistic models. But they assume that there is a probability of everything, and then they measure what is the probability they are losing money, right? And they price it accordingly, right? Okay, so sometimes it's usable to model a continuous system, so an infinite dimensional system, into finite state machines. And what you do is that you can discretize, for example, space, right? So in the hill climbing robots, you can say instead of having a continuum that tells you the position, you can overlap a grid, and then you can say the only information you want is that I am in this block of a grid, or I'm in this block of a grid, or I'm in this block of a grid, and so that becomes a discrete. So it becomes a finite state system. Now this one is, and this is real. So this one is actually a finite state machine that represents an engine controller. Okay. Now, interesting point. Now, if you follow this from Delphi, now if you put all of the things that you see on the node are the description of what the state is, and the arcs are labeled, the guards and all of that. What happens if you take this action, or the other action. Now, it's interesting because this is indeed a finite state machine, and it's given the control to the spark plugs, the ignition, and it's giving you the control over the injection, how much gas you inject into the cylinders, right? And when you hit the spark inside the engine, okay? So this engine control does all of this. Now, the interesting point is that if you look at the actual system, the actual engine is a discrete system or is a continuous system? So the movement of the pistons is continuous, right? So the representation of the control action is discrete, but the actual this is called hybrid system. So there is a piece that is continuous and a piece that is discrete, and this is a piece that is discrete. It represents and summarizes the behavior. This one are the initial state, the input, output, transition, usual stuff. Now, there is also an actor model of finite state machines in which you can hide the state inside, and you can represent the behavior of finite state machine as a set of function at the input, function at the output, and that finite state machine is a mapping of the space of the input into the space of the output. Now, in this particular case, I wouldn't possibly use this model, but you could use it. And it's particularly useful to combine finite state machines, but you lose all the advantages of finite state machines. So don't do that, in my opinion. So what we'll be able to do with finite state machine, a way to represent the system for mathematical analysis so that a computer program can manipulate it, a way to model the environment of a system, as we said before, a way to represent what the system must do, and must not do, so as a specification, and a way to check whether the system satisfies its requirements in an operating environment. Okay? So, finite state machine is good. Now, can I represent everything as a finite state machine? Too bad, no. Okay. So, but it's a nice model. Every time you can use it, please use it. Okay, next time.